All right, so today we're going to talk about basically how scheduling works in manufacturing system, and also I'll present some of the typical problems that in some especially some simple problems related to scheduling in production companies. And then we're going to discuss some of the priority rules and how to make scheduling in job sequencing. First, let's look at some terms about scheduling. Uh, so first one is infinite loading. So infinite loading means the work is assigned to a work center based on what is needed. What it means is that there's never a capacity limitation, and whenever the work is received, you can always put it on the line and let it start to work. So that's called infinite loading. Means there's no limitation or consideration of the capacity to make it. Next one is the finite loading. Finite loading means there are some of the limitations related to scheduling, either because of the resource or some other limitations. In finite loading means we have to schedule each of the resources using the setup and runtime required for each other. Right? For example, if you are producing TVs, right, and you have a certain set of machines and different labor, then you have to coordinate all the machines and labors to make sure it goes through all the processes at a certain time in order to deliver the orders. So that's finite loading. And next one is the forward scheduling. Forward scheduling means the system takes an order and schedules each operation that must be completed forward in time. What it means is that same if you are if suppose we receive the order from a customer that we need to make 100 TVs at the beginning of this week, and then I first gonna look at when can I put my line, when can I put this order on line in order to make it finish this order as soon as possible. So this is a forward scheduling. Forward scheduling is compared with backward scheduling. Backward scheduling means I received the order and said that the order needs to be filled by the end of this week. I'll start to look at the end of the week. That's the deadline. And then in order to finish the deadline and look at what is the due date for the second last process, and then look at what is the due date for the third last process, until I can come back to the first process, say, hey, what is latest time that I need to start, right? What is the latest time that I need to start my order in order to finish before the deadline? So that's backward scheduling. Forward scheduling means when can I put it on the line as soon as possible. Right? I won't care about what is the deadline. I only care about when can I finish this, or when can I finish this order as soon as possible. All right. So when we're doing scheduling, of course, there are certain limitations, and some of the limitations are related to machine. So we call it machine limited process, which means that the equipment is the core or the most critical resource that is related to scheduling. Because if we have to schedule the order or activities around the machine limitation. Well, another type of limitation is the labor limited process, which means that labor is a key resource that is we need to schedule the order around. Well, in most of the cases, that either it is labor limited or is machine limited. All right, now let's look at for different type of manufacturing process or systems, what is a typical scheduling approach that we have to utilize? First one, continuous process. So for continuous process, usually this kind of processes that are dealing with some chemicals, steel making or wire making, or or some liquids like the medicines, beer, soda, or canned food, right? Food processing. So these kind of products really requires a continuous process. It's hard to tell a single unit. Right, it's hard to tell a single unit, because, for example, if you are making a car, then that's discrete, right? If you are making TV, or keyboards, or computers, you can tell from one unit to another unit, but in a continuous process, it's hard to tell, and it's always continuous. So, and the characteristics for this kind of process is that usually it's full automation, and it's really highly automated and requires very little labor involvement, and because it's all automation. And in order to schedule this kind of process, usually it has to be a finite forwarding scheduling, because of the machine machine is a key resource in scheduling. So whenever you need you have an order that is for a certain amount of orders, then you have to look at if the machines or the line is actually available in order to put the order on the line. Well, the next type is high volume manufacturing. We have seen a lot of products actually come out from high volume manufacturing. For this kind of high volume manufacturing process, a typical characteristic of this is that they have very limited models, and it's really high volume production. For example, the iPhones, right? Or iPhones, iPads, keyboards, TVs. Usually they have very limited models, and all the setup, all the configurations of the production line is exact the same. You do not need to change setups. So sometimes they might have to, give different colors, but that's very limited modification or changing the setups. For this kind of production, it's also highly automated, and also sometimes it may require a little bit of human involvement in order to work with the machines to make the process happen, and in this case, most time it's most time that it requires the equipment in line or form a production line. Well, for this kind of process, for the scheduling, it's also the finite forward scheduling of the line, and also the machine is limited, because whenever we have this highly automated equipment, usually the machine is the limitation of the resource. And the next one is the mid-volume manufacturing. For this mid-volume, usually it's because it has the volume is not really high. Sometimes it has customizations, or they are made for specific needs, right? So for example, high-end consumer products, industrial parts, right, needs a lot of modifications or different models. So for this kind of mid-volume manufacturing, usually we use group technology, right, or cellular manufacturing. So we can make customizations or quickly change the configuration or setups in order to make different models. So that's why it says focus on manufacturers. So focus on manufacturers means those little factories, or I'll say little production lines, can quickly be modified or can reconfigured in order to make some other models, or make even some other products. Well, for this kind of scheduling, usually we use infinite forward scheduling typically, and they are also mostly it's actually labor limited. The reason is the labor limited because it involves a lot of labor intervene into those customization of the changing of the setups. And the next one is the low volume work centers. So low volume work centers is that's compared to mid volume manufacturing, that's even more customization, and also the volume is a lot less than the mid volume manufacturing. So in this case, usually that's prototyping equipment, or just making a certain kind of model, or even project based production. And those are the typical situation with those processes are they are machine centers organized by manufacturing functions, right? Not in the line production line, but in different functions. For example, cutting, or welding, or painting, different processes. And of course, in the low volumes work centers, human actually is a key resource in production, and also the in production cost. And for this kind of scheduling approach, usually we have it's infinite forward scheduling of jobs. So it's infinite because whenever we have this kind of job, we can always modify our production lines, or just put it on the line and let it start to process, because our work centers have fully flexibility in order to make different models of the products. All right, so then next, let's look at the functions of scheduling. So the reason we need to do scheduling in production is because we want to have a better allocation of orders, equipment, and personnel, right? And also we want to determine the sequence of order performance, initiating, performing the scheduled work, and how to control the shop floor. I'll give you one example so you can understand why scheduling is important in production and how scheduling works. So for example, okay, you and your whole family, right, are at home. Well, in your family, in the house, there's only one desktop and one iPad. All right, so four of you, right? Your father, your mother, you, and your sister, right? Each of you have your own tasks to do online in order to submit your assignment or your work, or your other job duties, but by a certain due time. For example, you have to submit your homework by 11:59 p.m. Well, your father have a job to be finished by 8 p.m. Right, and then your mother have something else. Then your sister have another homework to submit. Well, you only have one desktop and one iPad to work on this. And iPad, if you work on iPad, it actually is a lot slower than desktop, but it's better than not having anything to work. Well, in this case, you have to look at, okay, so who is the due date? Due time is earlier, and how much time it takes, right, to complete your assignment, right? You don't want to have your sister, waited too long. Actually, maybe she only needs 10 minutes to finish her assignment, right? So in this time, you have to figure out what is the best way to sequence the work and to assign the resource, the time to each of you in order to let everyone finish their work. So this is how same thing how scheduling works in production companies. When we receive the order, then we have to find out, okay, how can I make this order that as soon as possible, and also it will not affect other orders, right? Because we need to look at the deadline, we need to look at our availability of the equipment, and also the labor, and also other resources, right? So this is how the scheduling functions in the production companies. All right, so some of the objectives that the work center scheduling we want to meet, the goals are, first of course we need to meet the due dates, and also we want to minimize the lead time, minimize the setup time or cost, because we do not want to spend a lot of time doing setup or reconfiguration, and because that is all time and also money. And also when we are scheduling work, we want to limit or reduce work in process inventory, because if the parts are not moving on the shop floor, it means we are losing money, right? So we do not want to have the parts sitting on the shop floor for a long time. and of course, maximize machine utilization. All right, in terms of some typical rules for scheduling, and this list talks about some very common ones, right? The first one is first come first serve, right? And so basically, order whenever orders are received the first, then we want to run the order first, right? And also the next one is the shortest operation time, means we're gonna sort all the orders by its operation time. If the order requires the really shortest operation then we're gonna have that order finished first. Then we're gonna keep the longest operation time to the last. Well, the third rule is earliest due date first. Means we're gonna sort the orders based on the due date, right? For example, if you have a due date tomorrow, then we probably have to run that order first. If we have a due date maybe next month, maybe we want to keep that order later. But of course, we have to look at what is the how long we need to keep. We need to work on that process on that order. So that's why we have another rule, which is the fourth one, is select time remaining. So select time remaining means we're gonna look at the difference of time remaining before the due date, right, and the remaining processing time, right? For example, the order need to be finished by the end of Friday. And the processing the order actually only takes 1 day, then we can just calculate what is the select time, right? If it is now, it's only Monday morning, it means we have another 4 days, right? All right, another one is select time remaining per operation. So basically, it's ordered with the shortest select time per number of operations are run first. So A equals to the select time remaining, right? Select time remaining divided by number of remaining operations. How many operations left? The sixth rule is critical ratio. So critical ratio is calculated as the difference between the due date and the current date divided by the number of working days remaining, right? For example, okay. The order needs to be completed by Friday, and currently it's Monday, but actually there are a couple of days that is holidays during this week, means we only have probably only 2 days, right? We only have 2 days left to finish those work. So that's how we calculate how critical the job order is. And the seventh rule is last come first serve. So last come first serve means of course which order comes last, gonna serve it first. So the reason they have that is usually when the order arrives, it's always placed on the top of the stack. So the operator only see that and then pick that first to run it first. It also happens a lot. And the last one will be random. A random order will be, it really depends on the supervisors or the operators, when they look at the different orders, if they feel that they are more comfortable to work on some of the orders and finish them quickly, then they probably just choose that. And so that's, this type of scheduling is called a random. Now we talk about many different scheduling rules. It's not that you have to use them all the rules at the same time. Sometimes you only use one rule, right? And actually a lot of times you only use one rule, maybe combine one or two. Then I'm going to use some example to see how these rules are used in production companies. All right. So in terms of the measures of the scheduling performance, because we have to see if our scheduling works effectively or not, right? How to measure those performance. First, we want to make sure that we all meet the due dates, right? There's no lateness. If there's lateness, means our schedule actually failed. And also be minimizing the flow time. So we want to have this order to be within our company as short as possible, right? For example, you receive the order on Monday, and if you can get this order up, by early Tuesday, then that's only staying in our company for 1 day. It's a short flow time. But if you it's the same situation, but you finish the order actually by Thursday night, means the flow time is actually 4 days, right? So that's longer than Monday morning. And also next one is minimizing the working process inventory. You're gonna look at if there are a lot of WIP or working process inventory on the shop floor, and also look at if there are a lot of idle times of the machines, right? For example, we are all working on this order, and then the other machine will have to wait for a long time before they can process this order. Well, in this case, there are some idle time, and that's also something we do not want to see in scheduling. All right, now let's look at one example. This is problem 1. So this kind of problem is a typical problem that n jobs on one machine. So we have n multiple jobs, but only have one machine. Then we have to look at, okay, how can I, what kind of a sequence should I choose in order to have all the jobs to go through this machine effectively, and also with meeting the requirements, with no lateness, low flow time, less WIP. Yeah. So, for example, in this example, there are A, B, C, D, E jobs, right? For each job, there are processing times on this machine. So, A requires 3 days to be processed on this machine, and its due date is 5 days, right? 5 days from now. And B arrives a second, and then requires 4 days to be processed on this machine, and the due date is 6 days. And C, constantly going to see how much time it takes on this machine, and also what is the due date. Well, for this kind of typical problem, it actually happens a lot in not only in production companies, but also in service, right? For example, in the bank, right, or DMV, or in any other lines of waitings, it happens. Well, let's first look at, if we use first come, first serve rule, what's going to happen? If it's a first come, first serve, we're going to use the sequence of A, B, C, D, E, right? Because the order arrives in this sequence, A, B, C, D, E. So we're going to use the same sequence, A, B, C, D, E, and then we list the processing times, right? And then we'll look at their due date 5, 6, 7, 9, 2. And then we're going to calculate the flow time, because flow time is a key measure, right? Key measure of our schedule effectiveness, okay, performance. All right, so for job A, the flow time is 3 days. It's because it takes 3 days time to be processed on the machine and then get delivered, right? So that's why it's flow time is 3 days. Means the order stays within our company for 3 days. Now let's look at B. Okay, we receive the B, right? Beginning of Monday, beginning of the Monday. It actually takes what? It takes about 7 days to be finished, right? From our production line. Why? It's because order B or job B comes a second to be processed. So B has to wait for 3 days until A is finished. Can A start its job, right? So that, and it takes about another 4 days. So it's 3 plus 4 times equals to 7, right? So for example, if I'm order B, then I have to wait 3 days later. Right now, I finally can be processed on the production line, and when it's finished, it's actually already 7 days on the within the company. So that's right, 7 days. Consequently, we can calculate C, D, and E, right? C has to wait for another 7 days until it can be started. So that's why C requires C's flow time is 9 days, and D's flow time is 15 days, and E's flow time is 16 days. All right. Another indicator of performance is mean flow time. So mean flow time means we look at the mean, all right, or what is the average. So we can calculate all the flow times added up all together. So all of the flow time added up together means we're gonna look at flow time A is 3, flow time B is 7, flow time C is 9, flow time D is 15, and flow time E is 16. We added up all together divided by how many jobs, right, or how many orders. How many jobs, how many orders? Be divided by 5 equals to 10 days. So it means the mean flow time for this kind of scheduling is 10 days, right? 10 days. All right, now let's look at our result here. All right, so for example, for A, the flow time is 3 days, right? And the due date is 5 days, which means what? Which means we actually finish this order or finish this job ahead of due date. Means we're good. But for B, we got a problem. B's due date is 6 days. We actually, the flow time for the B is 7 days, which means the order actually is within our company for 7 days before we can finish. Means we already passed the due date by 1 day. Right, so this is called lateness. Lateness is a flow time minus the due date. It's 1. Let's call it lateness. Right, this is 3 minus 5. If it is negative means we're good. Actually, it's 0. I'll just use it as 0. Let's say lateness. This is 0. Then this will be a 7 minus 6, 1. It's 9 minus 7, 2. 15 minus 9, 6. And this is a 16 minus 2, 14. So you can see actually there only one job is not late. All the other jobs are actually late. So probably gonna figure out that maybe the first come first serve rule might not apply well in this case, right? In this case. All right, so we use the first come or first serve rule. Now let's look at the shortest operation time, right? So shortest operation time means we're gonna sort the job or job sequence by from the shortest operation time. Now, after looking at A, B, C, D, E, we know that E actually only requires 1 day to process. So we're going to process E first. And then C requires only 2 days. We are going to process C first. Then we come out the sequence of E, C, A, B, D. Now, let's do the same thing. You got a process time, you got a due date, right? Then we can calculate the flow times for E, C, A, B, D. Then flow time will be 1, 3, 6, 10, and 16. Right? And then also going to calculate the mean flow time is actually only 7.2 days. You can see compared to first come first serve rule, the mean flow time for ISAT scheduling is actually shorter than the first rule. Right? Now let's look at the lateness. All right, lateness for this rule for E is what? The flow time is 1. Actually, the due date is 2, means we're good, right? Limit is 0. And the C, flow time 3, and due date is 7, means we are good. And then A, flow time is 6, due date is 5, late by 1 day. And this is late by 4 days. And this is late by 7 days. Right. Also, we are looking at lateness compared to the first come first serve rule. It is also performs better than the first come first serve rule. All right, so let me see. Let me see what happened. All right. Now let's look at other rules, how other rules apply in this case. Earliest due date. We'll do the same thing. Earliest due date. I'll look at which order or which job has the earliest due date. You can see that the sequence is E, A, B, C, D because E has the earliest due date, which is 2, right? And then also we'll calculate the flow time. Then calculate the mean flow time is 7.9 days. And our prior exam one is 7.2 days for the shortest operation time. Then let's look at the lateness. So lateness for this case is this will be 0, this will be 0, this will be 2, this will be 3, this is 7, right? The next, let's look at the last come first serve rule. What's going to happen, right? Last come first serve rule, same thing. We find a sequence and then we calculate the flow time and then we look at the lateness. So lateness here is 0, 0, 2, 4, and 9. Okay. Sorry, this is 11. This is not 4. This is 7. And also, random rule, select time remaining. So random rule, you can randomly choose a sequence here. Well, for the select time remaining, when you have to look at, okay, now we have this, processing time, we have this due date, then we can calculate what is the select time, right? So select time will equals to the due date minus the processing time. 2 minus 1, 1, 5 minus 3, 2, 6 minus 4, 2, and then the C is 7 minus 2 and 5. So we rank them based on the select time remaining, right? So E, A, B, D, C, and then we can calculate what is the flow times in this case, and then actually the mean flow time is 8.6 days. Okay. All right. We used different rules. Now let's have a comparison of all these rules. Right. We use the first come first serve, shortest operation time, earliest due date, last come first serve, random, and shortest select time remaining. So let's look at the flow times, right? Flow times. This is the first come first 50, and the shortest operation time is only 36, right? Well, let's look at mean flow times. What are the shortest mean flow times? It's these two, right? And also the total flow time, also these two, right? And now let's look at the average lateness. Same, these two rules generate better. And compared to shortest operation time and earliest due date, actually shortest operation time has has a better performance than earliest due date, and also other all the other rules. Probably in this case, we can choose shortest operation time as our rule for scheduling. So this is how we deal with n jobs on one machine, and how different priority rules can be used in order to have a better scheduling performance. All right, now let's look at another problem. Is n jobs on two machines, right? So there are maybe 2 or more or 4 or even more jobs on two machines. Means what? I mean 2 or more machines must be processed on two machines in a common sequence. Right, in a common sequence. Means what? Means there are machine, say there's machine 1 and also machine B. No, sorry, machine 2, right? And jobs can be A, B, C, D, and even more, right? And so A needs to be processed on machine 1 with the processing time of T, say TA1. And this will be processing time A2, right? This will be TB1, TB2, TBC1, TC2, as TD1 and TD2. All right, so all the jobs needs to be finished, and all the jobs needs to be processed on the two machines in the common sequence. And then the question is, how do we schedule the job? Should they be A, B, C, D, E, or should they B, C, D, E, or should be in some other sequence in order to have a better performance in this case, right? So our job is to minimize the flow time from the beginning of the first job to the finish of the last job, right? You can actually see it's actually challenging because when we have two machines and all the job has to go to the two machines, then we really need to find which job we need to process first. Why? Let's show you one example here. All right. For example, we have this Gantt chart with machine 1 and machine 2, okay? And this is the timeline. All right, so for machine 1, let's start with job A, right? So job A needs to be processed on machine 1 first. And then right after the job A is being processed on machine 1, it can start to be on machine 2. Okay. If on machine 2 it actually takes a longer time, right? This is A. So after A, what happens is on machine 1, right after job A has completed this process, we can start another process, right? Another job. For example, this is let's start with job C, okay? Job C. Okay. Then after job C, we can do job D. But what happens is that here, job C can only start its second operation until what? Until job A actually finished. It's on the machine 2, right? This is job C. This is job C. It's job C. And then same thing, D will have to be after this. D did. So the job is, so the goal for this scheduling is we want to find out how can we schedule the sequence of A, B, C, D, E in order to have the shortest flow time, right? Flow time. Shortest flow time. Because let's look at one case. So what happens if A only requires, let me change another color. A actually only requires this little time for machine 2. And in this case, what happens is C can only start on machine 2 at this time because C cannot even finish the first process, right? First machine by this time. If this is a C, right? Same thing, D probably in this way. Because D cannot be processed on machine 2 until D has finished on machine 1. In this case, what happens is that you can see there are some of the time are actually the machine is idle, right? The machine is idle. So our job is to find with the smallest idle time, as possible, right? So this is about n jobs on two machines, All right, now let's look at how do we solve this problem. Actually, we have a rule to deal with this. It starts from the mathematical equations, and it's called Johnson's rule. So Johnson's rule is that we're gonna first list all the operation time for each job, and then select the shortest operation time, and then if the shortest time is on the first machine, we do first. If the shortest time is on the second machine, we do the job last. If it is ties, we'll do first. Then we're going to repeat all the steps and then for remaining jobs. So how it works, now let's look at one example, this example. So this example that we have 4 jobs, and then we have 2 machines, machine 1 and machine 2. For job A, so the processing time of machine 1 is 3, it can be time, it can be minutes, hours, or days, whatever time unit. And there's 3, 2, and B on machine 1 is 6, then B on machine 2 is 8, and C is 5 and 6, and D is 7 and 4. Well, now we get to this issue. Then we have 4 slots. So this is our sequence, job sequence. According to Johnson's rule, we first gonna look at what? First gonna look at the smallest number of the 2 columns. Right? This is column 1, this is column 2. The smallest number of the 2 columns, which is 1. Which is 2, right? Which is a 2. So if it is 2, is on the second machine, right? If it is on second machine, we put it last. So this 2 is actually job A. So that's why we put job A last. Understand? We look at the smallest number of the 2 columns. Smallest number of the 2 columns is actually 2. 2 is a job and it's on the second machine, so we put it last. Then next, smallest number is what? Is after this, it's actually 4, right? It's 4. So 4, because it is also on the second machine, so we're gonna put it here. Then after 4, we only have BC left, right? We put C here, because 5 is the next one. And then last one is 6, right? So this is how we assign these n jobs on 2 machines with Johnson's rule. We're gonna look at the smallest number of the 2 machines, and then assign it to the last if it's on the second machine. If it is assigned in the first, if it is first machine. Okay. All right. So this is how it works. With what shows up on the Gantt chart. With that example. For the example, you can see there are actually no idle times between during this time and during this time. So which means this is a better solution, optimal schedule solution. All right. So next, let's look at what another type of problem is n jobs on n machines. So and n has to be the same number, right? N jobs on n machines. So for n jobs on n machines, usually we use a matrix to convert some of the matrix in order to solve this problem. So what happens is that, for example, we have n jobs, and so jobs 1, 2, 3, 4, 5, but also have n machines A, B, C, D, E. We need to find one combination, right? We need to find one combination. Should job 1 be processed on A? B job 2 processed on B, job 3 processed on C, job 4 processed on D, and job 5 processed on E, or we have a totally different combination, right? For example, maybe job 1 processed on E, and this combination, we need to find a combination that results into into an optimal performance. So optimal performance can be the smallest number of cost, right? The lowest cost. For example, maybe you can find, okay, suppose one for first job, let's process on B, second job process on D, third job process on E, and then fourth job process on A, and then fifth job process on C. So if this is a optimal solution, it should result into the lowest, right? The lowest cost. If it is an optimal solution or not, I don't know. I'll give you just a random sequence, right? But our goal is to find this combination that will result into the lowest cost. Well, in this case, what is the cost, right? If job one is processed on B, then that's $6. If job 2 processed on D, that is $8. If job 3 processed on E, then that's $4. And if job 5 processed on A, then that's $7. If job 4 on A. If job 5 on C, that's $4. Well, in this case, the cost for this scheduling will be what? 6 plus 8 plus 4 plus 7 plus 4, right? Then there will be 10, 12, 22, 29. This will be 29. Then maybe there's another combination that actually resulting to a much lower cost. But our job is to find out what is the best combination that results into the lowest cost, right? All right. Then, how do we solve this kind of problem? Now let's look at this. The first step of solving this problem is we're gonna do row reduction. So row reduction means we want each row actually has 1 0, at least 1 0. Each row has at least 1 0. Now this is our original, right? So this is our original matrix, right? You can see the first row is 5, 6, 4, 9, 8, 3. The second row is 6, 4, 9, 8, 5, and but there are no zeros. There's no zeros. But the first job is to make sure each row has zeros. So how do we find zeros in each of the row? When we do row reduction means we're gonna have each row to minus its smallest number, right? For example, this row 1, smallest number is 3. We're gonna use all the numbers minus 3. 5 minus 3, 6 minus 3, 4 minus 3, and 8 minus 3. Then we get this first row, 2, 3, 1, 5, 0. Then the second row here, the smallest number is 4, right? We're going to use, and also make sure this is minus 3, right? So 6 minus 4, 4 minus 4, 9 minus 4, 8 minus 4, and 5 minus 4. Then we get the second row here. 2, 0, 5, 4, 1. Consequently, we can do the rest of the row reductions, and then we get this matrix. Okay. All right. Now after this conversion, row reduction. We can find at least 1 0 in each of the rows. Okay. So then our next job is to make sure each column also has at least 1 0, right? So this is the result from our prior step after row reduction. Now let's look at if each of the column has at least 1 0. First column, yes. Second column, yes. Third column, yes. But the fourth column does not have any 0. So in this case, we'll do a column reduction. So column reduction is similar to the row reduction, means we look at this column, right? Look at this column and then find the smallest number, which is 2, right? And have this all the numbers on this column minus the smallest number. Then we got 3, 2, 1, 1, 0. If there are more columns without zeros, then you can do the same thing, right? In this case, we only have a column D that does not have 0, so then we only need to do the column reduction for column D. All right, so now we have at least 1 0 for each row and also at least 1 0 for each column. Then next thing we want to do is to apply line test. So line test means we're gonna use the minimum number of lines to cover all zeros in this matrix, and all the lines has to be what? Has to be either horizontal or vertical. You cannot just get a line which is this way. That's not acceptable. All right, so then we can see in order to cover all the zeros, we only need actually 4 lines. We only need 4 lines. You can try actually. The minimum number of lines to cover all the zeros is actually only 4 lines. Well, in this case, we haven't reached our optimal solution yet. Why? Because we will need 5 lines. Why is 5 lines? Because we have 5 jobs, right? If we have n jobs, then we need n lines, right? So because we have 5 jobs, so we need 5 lines to cover all the zeros. But currently, the minimum number is only 4. So which means means we'll need more zeros. Then how do we create more zeros, right? How do we create zeros? Somebody really smart is gonna say, hey, now let's just minus the smallest numbers, right? All right, but how do we do that? Then we're gonna look at this is the matrix from our prior step, okay? And then we're gonna look at all the numbers that is not covered by the lines, right? All the numbers that are not covered by the lines. There will be 2, 2, 1, 5, 3, 2, 5, 2, 1, right? And then we're gonna find the smallest number of those numbers. Those uncovered numbers. The smallest number of those uncovered numbers is what? Is 1. Right? It's 1. So we're going to have all these uncovered numbers minus the smallest number. Right? So 2 minus 1, 1. 2 minus 1, 1. Right? And then 5 minus 1 will be 4. 1 minus 1, 0. 5 minus 1, 4. 2 minus 1, 1. And then 3 minus 1, 2. 2 minus 1, 1. And then 1 minus 1, 0. Now we actually created 2 more zeros. Okay? Which means we'll need more lines to cover those. All right, so in this case, someone actually noticed that in this example, they actually also minus the 1 with all the cross-sectional numbers. These numbers also minus 1, right? Plus 1. Plus 1. So you can see 1 plus 1, 1 plus the smallest number is 2, and then 3 plus the smallest number is 4, right? 2 is converted to 3, 2 converted to 3. Well, in this case, it actually does not really affect the result, right? If you do this, plus or not, it doesn't really affect the results. But because all our goal is to want to make sure we have created more zeros for the rest of the numbers. Okay. All right. So after we got this, we're gonna apply another line test. Now this time we actually need 5 lines to solve this problem, right? 5 lines to solve this problem. All right. If the smallest number of covering all zeros is actually 5 lines, means we have reached our optimal solution. Okay, we have reached our optimal solution. Then what is our optimal solution? We're gonna look at zeros. Let's see, job 1, right? Job 1, we have 2 zeros, means it can be processed on both C or E. While job 2, right, has only 1 0 at the machine B, means it can only be processed on B, right? Only option for B is B. And job 3, the only option is to be processed on C. And job 4, the only options are B and D. And then 5 will be A and D. So the solution will be simple because 2 and 3, there are only one option, right? So 2 has to be what? 2 has to be B, and 3 only option is C. Right? Now let's look at 1. Because C is already occupied by job 3. Then job 1's only option becomes E. Right? It becomes E. How about 4? 4 has options of B and D. Because B was already occupied, now the only option is D. And then job 5, the option will be A. So this is our final solution. This is how we find out our final solution. Right? Look at the zeros. Where are these zeros for this job? And then find out the solution. Then we go back to our original cost matrix. Do you still remember the original cost matrix? Right? Original cost matrix is what? Is this matrix, right? It's this matrix, very first matrix with cost numbers. Very first number matrix with cost numbers. Right? We actually, with our optimal solution, our cost is $17. So this is how we solve this kind of n jobs on n machines. So another similar problem will be the transportation problem. For example, you have multiple trucks, right, to deliver products, and then you have different destinations, and for each destination with different truck, actually the transportation cost will be different, and then you can create this matrix and then figure out what is the best combination in order to reduce all the transportation cost, right? So this is a typical problem that you can use matrix to solve it. All right. Lastly, we're going to look at some of the concepts related to shop floor control. So shop floor control, it means as a production manager, you have to look at how efficiently your production system is running, right? Especially related to scheduling and also some other operations. And so major functions for shop floor control includes assigning priority of each job order, shop order, and maintaining WIP quantity information, and also conveying job orders status information to the office, and providing some output data for capacity control purposes, and providing quantity by location, by shop order for WIP inventory and accounting, and providing measurements, efficiency, utilization, and productivity. So basically, these are probably the job duties for a production manager or production engineer, that what you need to do in order to keep your job, your production shop floor running. And so a chart will be the Gantt chart. I already used the Gantt chart to demonstrate, for the Johnson's rule, and then how to do that. So Gantt chart means it includes kind of two axes. The one axis is the time axis, another axis will be the job axis. Right, so you use these two axes to show how long it takes, for each of the job on different timelines. Right, so this is how we draw the Gantt chart. So there are a lot of softwares have the tools of drawing Gantt chart. You can use those tools to demonstrate how to how to schedule jobs, and also how to look at how efficient your schedule is. And also a lot of times when you are doing planning, it's the same thing, right? For example, you want to plan your project, right? Then you have the initiation, your teamwork, and then finish the first step, second step. Then you can use the Gantt chart to do the planning. And another is the tool. Some of the typical tools that are being used in the shop floor, it actually differs a lot. With different production companies, then I use different tools. One typical tool is the dispatch list. So it includes reports and also a lot of other things. For example, the reports include the scrap report, rework report, shortage list, performance summary reports, and this is the one. One report of the dispatch list. You can see that dispatch means this is jobs, right? Jobs need to be finished, and the description of the jobs and also run times. And in actual production companies, actually can differ. Sometimes it gonna list different jobs and then give you a very detailed information about about the descriptions and also what time it need to be processed on one machine, right? So that's more detailed job order. People call it job orders, and those job orders either can be conveyed on the shop floor with some physical papers or with on the computer. Right. So for example, you can log in the system. You can actually see the jobs you need to complete it today at your process. Also, at the shop floor control, you can also you will need also to come up with some of the daily reports, like delay reports, scraps or other things, right? So these are some examples. You can see how you can report those situations. Again, there's no uniform format. It has to be, but these are reports that are typical activities that you need to know, because these reports, this information actually convey data or convey information for your decision making in order to make your production company more efficient, right? So someone can make analogy of the shop floor control as this kind of a low inflow and outflow. So the inflow will be the new orders, and outflow will be the completed orders. Then your job is how do you control this kind of faucet, right? So that's a production control. So you can control, or you can try to minimize the working process, right, on the shop floor. If it is keep all running, means it's really low and it goes out really fast. If it goes fast, means what? Means your lead time, manufacturing lead time is really low. And lead time is low means all the job orders will go through a production company really fast, and then you can always deliver better performance for the orders. All right, so this is production and shop floor, and lastly, gonna list some of the principles of work center scheduling. So there's direct equivalence between workflow and cash flow. Same, because all times are money, right? And also effectiveness of any job should be measured by the speed of flow through the shop, and schedule job as a string, and with process steps back to back. And once the job has started, please do not interrupt. Okay? Speed of flow is most efficiently achieved by focusing on bottlenecks of work centers. Right? So if you see any kind of bottleneck or some idle times of the processes, then you probably want to find out, okay, where are there bottlenecks, and then use some of the cycle time analysis or find some ways to reduce that, right? Either implementing better technology, or getting more machines, or split the jobs, multiple ways to do that. Also reschedule every day, because it's actually the something happen on the shop floor changes all the time, right? There are some delay, there are some kind of problem happen. You have spend time to solve the problem, so you have to. It's very dynamic, so you have to get timely feedback from the shop floor in order so to reschedule frequently. And obtain feedbacks on each day on jobs that are not completed at each work center. Understand why. See if you're then look at if your schedule is reasonable, or something happened on the process that really delayed the processing. And the match work center input information to what the worker can actually do. And then when improving output, look for incompatibility between the engineering design and process execution. So certainty of standards, routings, and so forth is not possible, but always work towards achieving it. So there's always the ideal situation, but also need to look at what is reality, right? But it's good to achieve all the goals. All right, so some of the takeaways for this class, it will be, understanding the meanings of the different term, infinite, finite, forward, backward, scheduling, and all these different rules. Understand how to solve those three key problems. N jobs on one machine, and then n jobs on two machines, and in the common sequence, and also n jobs on n machines. So scheduling is a very complicated problem. It's not only those three problems. It's a lot more problems. Sometimes you will add one more machine, it will become a totally different situation, and it requires a lot of different complicated schedule algorithms to solve those. But those the three problems are very common ones that will give you a good start to think about how scheduling works in production companies. So that's why I understand those. So you can enter in the door and explore more. Then understand the principles of the work center scheduling. All right, that's all for today.